and that somebody is requesting our data and to click the link if it's that. Oh, no, I just reported.
We're just going to wait another couple of minutes for others to join. There's another group coming in.
Okay, so go ahead. I'm looking at the magic. Okay, the magic class 4-7.
I'm gonna mute everyone, and Arnie.
Salut Martin. Oui, je t'entends. Toi, tu m'entends-tu? OK.
Okay, just another minute, and we'll get started. We've got. Well, let's go for it. I'm Ted Dangelmayer, and welcome to our webinar. I'm glad you could all join us, and we really encourage you to. I'm sorry, we're getting. I got one more thing to fix here. There we go. Okay, so we're going to show you this tutorial on static control in the clean room, controlling electrostatic attraction. And Arnie Steinman will be presenting. I expect many of you know both of us probably, but just to introduce Arnie briefly, he's one of the foremost authorities in ionization, and electrostatic attraction is certainly in his wheelhouse for similar reasons. He has had many years in clean rooms, not just hours, but years in clean rooms.
So true.
So with that, Arnie, I'm going to turn it over to you, and
well, let's see if we're working here. Nope, no mouse control.
Okay, I've let go of mine. You should have it momentarily.
Okay.
You have it yet?
Nope.
Well, actually, let me do one more thing while we're. Let me bring this over here. Let's see, look here, we got, I'm sorry, I have a new message that just came in, trying to figure out what. Okay, how about now? Let me let go of my mouse again. Try it now, Arnie.
All right, got it.
So just before Arnie presents his webinar, I want to let you know that we have another webinar in January on the 14th. And this is a particularly interesting one. It goes well beyond just a workstation setup. We get into some practical recommendations that we've learned over the years. There are some subtle things you can do that really make it much more effective. We do offer TR53 CDM certification, and that we generally do on site upon request. And then next August, we'll be co-hosting another in-person workshop with the Northeast chapter of the ESD Association. So with that, Arnie, I'm going to let you.
Okay,
Let me just add one more thing. I was starting to say earlier, we really encourage questions. And let's start with using the chat option, and then we'll toward the end, what we'll turn on the microphones and let you have a discussion with us.
okay, Ted.
Yep.
All right. Well, as you've seen, we're going to talk about static control in clean rooms and how you control electrostatic attraction. That this is the other part of the static control problem that we seek to solve. We certainly are aware that ESD is a problem, but ESA is also a problem because when you have static charge in a clean room, it can defeat some of the methods you're using to keep the air clean and keep the room clean. So controlling static charge is an important part of controlling the attraction of particles to critical surfaces in the clean room. So many industries require clean manufacturing. We're seeing more and more products that are made in clean rooms because they're becoming more and more technologically advanced. And to be able to keep those technology advancements, we need to have a clean manufacturing area. But with clean manufacturing, you also find you have lowered humidity levels, you have process required insulators, you have ultra clean surfaces in the clean room, and you have processes which involve product movement, and there's a lack of naturally occurring air ions. This is because you're passing the air that goes into the clean room through many, many ducts, metal ducts. And the result is that under normal circumstances, there are very few ions that come in with the clean room air. And that can be a problem, as we'll discuss as this webinar progresses. All of these items can be contributors to elevated static charge levels in the clean room. That lower humidity, higher static charge, process required insulators, things that can charge and attract particles, ultra clean surfaces, which do not discharge. All of these things mean that you're going to have more static charge in and around the product in the clean room. So what we're going to talk about today is attraction, adhesion, and distance. These are the particle attraction mechanisms. We'll talk about some of the items of particle physics in air, deposition velocity. That's how fast particles are being deposited on a surface. They're due to gravity, to diffusion, and electrostatics. We'll see how these three methods of particles being deposited on surfaces, how they interact. We'll talk about electrostatic attraction, obviously, and we'll show you how we can calculate how we have what are the acceptable electrostatic fields. We'll talk about electrostatic charge generation. We'll talk about electrostatic deposition rates, and we'll talk about finally methods of reducing contamination deposition in the clean room. Clean room. What is a clean room? A clean room is a room in which the concentration of airborne particles is controlled. Makes sense. And which is constructed and used in a manner to minimize the introduction, generation, and retention of particles inside the room, and which other relevant parameters like temperature, humidity, and pressure are controlled as necessary. Now, this is the definition of a clean room that's in ISO standard 14644-1, which is called Clean Rooms and Associated Controlled Environments. And then part one, the -1, is the classification of air cleanliness. And we'll see what this standard recommends in that respect. So a clean room is a space that's isolated by a wall or a similar partition where the degree of cleanliness is achieved by air pressurization and filtration. So we have an incoming air supply. We filter it very highly with special filters, generally called either HEPA filters or ULPA filters. These are very high quality filters that take out most of the particles that will be coming in the air. We have a wall, we have balanced pressure, and we maintain an overpressure near the floor where the air exits the clean room. So this is basically a clean room. It's a box, filtered air coming in, overpressure in the room to keep particles from coming in from the outside. Now, for many years, the industry in the US at least used what was called Federal Standard 209E. And Federal Standard 209E, was an American standard, so it specified the number of particles per cubic foot that you could have in a clean room. Now, it was replaced by ISO 14644-1, and the ISO classifications are different, but they are also always talking about the same number of particles. 209 has been obsolete for many years, but its clean room designations are still used. We still talk about class 1, class 10, class 100. These are the 209E classifications. Now, the class 1 for standard 209E is the same as ISO class 3. So you see ISO class 3 is 1 particle per cubic foot. ISO class 4 is 10 particles per cubic foot, and these are measured at 0.5 microns. But the number you see there on the table is 35, and that's because we're not talking about particles per cubic foot, we're talking about particles per cubic meter. 14644 international standard always will be in metrics. So you have this table, you see how to compare things, and it tells you what are the allowable particle limits for each of the designations. So just remember, when we talk about class 1, we're really talking about ISO class 3 now. And with time, the 209E designations will eventually disappear, and we'll have just the ISO classifications. So what do we need in terms of cleanliness in our manufacturing? Well, depending upon what you're doing, the requirements for cleanliness will be different. You're doing chip module and bond and assembly, class 1000 to class 10,000, or ISO class 8 to class 7. You're doing 200 millimeter semiconductor manufacturing, you're typically in either class 1000 to class 1 in the federal standard, or class 6 to class 3 in the ISO standard. HDD assembly for hard disk drive, also ISO class 6 to class 4, or federal class 1000 to class 10. And finally, for 300 millimeter semiconductor manufacturing in integrated mini environments, we also are down at ISO class 2, which, if it existed, would be equivalent to the federal class 0.1. So again, depending upon the manufacturing you're doing, you will have different cleanliness requirements in your clean room. Static charge problems. Our static charge problems are basically contamination and ESD. We're not going to talk about ESD in this webinar, but we are going to talk about contamination control. So when we think about contamination, we think about the pellicles. These are the negatives that are used to put the patterns on the wafer. We talk about the wafers themselves. and we talk about equipment surfaces. These are all places where contamination can wind up because of static charge. And the thing to remember is that if you have charged surfaces present in your clean room, the attraction through electrostatics is generally greater than the airflow, the laminar airflow. And it will just, the static charge on surfaces will just pull particles out of the laminar airflow and deposit them on surfaces. That's the reason we want to control static charge, to reduce contamination. So electrostatic charge is a contamination, attraction is a contamination issue. It's a force. Electrostatic attraction is a force that can attract and bind particles to a surface. Electrostatic attraction can do this, and the reality is, once you have the particle on the surface, it's very difficult to remove. And as you can see, what we're showing here is you have your airflow, the particles are in the airflow, but if you have a charged surface, it will pull those particles right out of the airflow and deposit them on the surface. So electrostatic particle contamination is a combination of effects. You have electrostatic effects in the middle there. The result of that is attractive forces. You also have gravitational effects. You also have diffusion effects, and we'll show how those compare to electrostatics in a moment. The electrostatic effects create adhesive forces, which attract particles to the surface. Now, how do we know that charged surfaces attract particles? Well, many years ago at Analog Devices in Ireland, they did a study. They had an ISO class 3 mini environment, which is federal class 1. They put a 200 millimeter wafer in that mini environment, and they left it there for a while. So what we have here is, in fact, they did this with 2 wafers. The first wafer was held at 0 volts. It was not charged. And you see that after about a month, you still had particles on the surface. There are other effects besides electrostatics that will attract particles to the surface. And you see the number here is about 4,000 particles on the wafer surface as a result of it being just in that mini environment for about a month. In fact, it was 6 weeks. And 6 weeks is equivalent to 1 production cycle in the wafer fab. So this is, showing you what would happen if the wafer was in this mini environment for that production cycle. Now, the thing that they found also is a second wafer. They had a second wafer, which they held at 2,000 volts. Okay, same class 3 mini environment, same period of time, right next to the other wafer. And what you see here is you have 27,000 particles, almost 7 times as many particles were attracted to that surface. So they wound up with over 23,000 more particles on the surface. And the only difference between the 2 wafers was the charge on the second wafer. So we know that if we have a charged surface and we leave it in a clean room, it's just going to attract lots and lots of particles. So we have what we call the particle deposition velocity. This is the rate at which particles are deposited on a surface. We find that there are 3 major effects on this deposition velocity. We have gravitational effects, we have diffusion effects, and we have electrostatic effects. And all 3 of these affect the particle deposition velocity. The higher the velocity, the more particles that are deposited on the surface in a given amount of time. And we'll look at this in a little bit more detail. This is a chart that came from a researcher at IBM. And what you see here are the various effects of that cause particles to be deposited on a surface. Gravitational effects increase as the particle size gets greater. That's this red line here. We have diffusion effects. Diffusion effects are the blue line, and they increase as the particles get smaller. Okay? Now the green line here, which you can just see, is the are the electrostatic effects. And you can see those are here. Now, this heavy line here, this purple line, this purple line here is the combined gravitational, diffusion, and electrostatics. And what's really interesting is that when you get down below 1 micron in particle size, what you find is that the electrostatic effects really predominate. That we get down in here, you're looking at a line that's almost the same as that green line. So, and this is only at 200 volts per centimeter. If we go up to 2000 volts per centimeter, which is not an unusual number in a clean room to find on surfaces, we have this orange dotted line here. And you can see that this is very clear that, when you get down below maybe two microns in size, that electrostatics predominates. So electrostatics can be the most important part of the deposition velocity, and it really does affect the particles that are deposited on surfaces much more than any of the other diffusion or gravitational effects. Okay, so we want to reduce the deposition rate due to ESA. And we have an equation here. N is the number of particles that are deposited on the surface. And you see you have some things that you can control here. Now, the first thing, if you want to reduce the number of particles that are deposited on the surface, reduce C, the concentration of airborne particles. Obviously, the cleaner you make the room, the cleaner the surfaces will be. So reducing the concentration of airborne particles is the first thing you can do to reduce the particles on surfaces. Second of all, we have Q, the charge on the particles. If we get the charge off the particles, we get the charge off of the surfaces, we will reduce the number of particles that are being deposited on the surface. Then we can reduce E, the electric field. The electric field is the result of a charge Q that's on the surface that we're trying to keep clean. So if we reduce C, the concentration of airborne particles, if we reduce Q, the charge on the particles, and we reduce E, the electric field on the surface that we want to keep clean, these will all reduce the deposition rate of particles on the surface. And finally, reduce T, the time of exposure. That should be clear that you don't want to leave your product exposed for 6 weeks in the room, because you'll get a lot of particles on the surfaces, as we saw in the analog devices test. So how do we reduce E and Q? Those are the things we have, those are our electrostatic issues. Q is the charge on the particles, best reduced with using ionization. E is the charge on the surfaces that we're trying to keep clean. And, we can accomplish that by using standard ESD control measures. Prevent the surfaces from becoming charged. Ground them if they're conductive so that you can remove the charge from the surface. And finally, if they're not conductive, if you have an insulator, you can neutralize that surface again using ionization. So you have your standard ESD control measures that are used to control the static charge on surfaces, which will allow you to keep things clean. Triboelectrification. Triboelectrification is not your friend. Static charge is always generated when two materials are in contact and then are separated. You wind up with an equal and opposite charge formed on the opposing surfaces. Now, if one of those surfaces happens to be conductive, you can ground that surface, and the triboelectrification will only occur on the material that contacts the conductive surface. So that basically, whenever you have things moving, when you have contact and separation, you can get static charge being generated. The materials that we find in the clean room, and this list here on the right is many of those materials. They all encourage the transfer of charge through triboelectric charging. So whenever something at the top of the list contacts something at the bottom of the list, the item at the top of the list becomes positively charged, and the item at the bottom of the list becomes negatively charged. In clean rooms, you really wind up with a lot of Teflon and Mylar and polycarbonate, and these things that charge very easily when they contact other materials. So basically, a very interesting thing here is you never know what the charge might be. If your polycarbonate were to be contact quartz, for instance, the polycarbonate would charge negatively and the quartz would charge positively. On the other hand, if the polycarbonate was to contact the Teflon that was in the room, the polycarbonate would now charge positively and the Teflon would charge negatively. So you have no way of knowing ahead of time what polarity the charge will be. The only thing you know for sure is that if these materials contact and separate from each other, that you are going to get charge generated on those materials.
Arnie, we have
So-
a question. We have a question that
Sure.
came in.
Let's take the question.
For EMS production, normally clean areas are not needed. Is there any recommended class?
If there's no, I mean, it sounds like what you're saying is that there isn't really a contamination issue in this EMS production. And if that's the case, then you want to control static charge, if for nothing else, for ESD control. So that, you still, even though you might not have a contamination issue, you might have an ESD issue that needs mitigation through static control methods. I hope that answers the question. All right. I'm assuming it does, but we can go on here.
Thanks.
You're welcome. Some of the sources of triboelectric charging, you'll find all of these, are part of your clean room environment. When it comes to product handling, manual handling uses tweezers. There might be robots that move things around. You have tools like pliers that contact the product, and the product may, be, transported over rollers. This is all contact and separation, and it is a source of tribocharging. Wet and cryogenic processes, cleaning and etch, these are all, again, sources of tribocharging. Wipe down. That's the thing about clean rooms. Clean rooms have to be kept clean, and we are normally wiping them down constantly. There are ways to keep that wipe down from generating significant static charge. One of the ways is to keep the wipes moistened with either water or IPA, and that will keep the charge from being generated. But because you're doing wipe down all the time, this is a source of tribocharging. Some of the environmental issues that cause tribocharging to be at a higher level are low humidity and higher temperatures. These are all things that make the tribocharging worse, actually. Personnel moving, they might be in chairs. triboelectric charging when they move around in the chairs. They walk on the floors. That's a triboelectric charging mechanism. And they make contact the walls in the clean room. And the contact between their clean room garments and the walls may be a source of static charge. Product storage, again, you move your product in and out of carriers, you move it across work surfaces. Anytime you have motion, you have contact and separation, and you have tribocharging. And then finally, packaging materials. The packaging material itself may come in contact with your product, and it can be charged from that contact and separation. And then we use a lot of sheet protectors to keep track of what we're doing in the clean room. And basically those sheet protectors are a source of static charge. So lots of sources of tribocharging in the clean area. Cleanroom ESD issues. What are the issues here? We have many ESD sensitive products and they must be manufactured in clean environments. Examples are semiconductors, disk drives, medical devices, lasers, precision optics. These are all things that basically are need to be manufactured in a clean environment because particle contamination causes defects in these products. Now, as we talked about before, clean manufacturing conditions include lower humidity, process required insulators, ultra clean surfaces, processes requiring rapid product movement, and minimal naturally occurring air ions. These are all things that make the static charge problem in the clean room worse. All of these conditions, cause elevated static charge levels on and around ESD sensitive product. It's not only the product itself that becomes charged, it's the surfaces near the product, which can cause, with their electric fields, can cause the attraction of particles to our to our sensitive product. Handling plastic parts. You're wearing gloves. The plastic parts are a different material than your glove material. Even though the gloves may be ESD rated gloves, they still will cause tribocharging when you handle other insulators like plastic parts. You have plastic film that you may have to process, and it usually is transported over rollers, and the contact and separation between the film and the rollers causes static charging. A vibrating hopper. These are, using the vibration to cause the product to move, and all of that motion causes static charge to be generated on the product, on the materials that are in that vibrating hopper. So there they are. This is also a cause of static charge, and it needs to be mitigated to prevent the attraction of contamination. Water cleaning. Whenever you clean something with water and then spin the water off the surface, remember, evaporation is not a problem. It's the physical removal of water from the surface. What you see on the right here is what's called a spin rinser dryer. You put the wafers in here, you wet them down, and then you spin them to remove the water from the surface. And it's that spinning and removal of the water from the surface that causes the static charge. Routine cleaning. In the clean room, you are cleaning all the time. And the contact between the wipes and the surfaces is what causes static charging. As I mentioned before, moisten the wipes, IPA or water, you will significantly reduce the triboelectric charging that is occurring when you do this routine cleaning. Now, what we have in the clean room is ultra clean surfaces. You want to keep everything clean because if the surfaces themselves are not clean, they can transfer particles to your product, and that's not what you want happening. Clean room protocol typically calls for frequent cleaning of surfaces. And the result of this frequent cleaning is that it minimizes the conductive film of contamination that helps dissipate static charge. In other words, contamination has an upside in that it's generally tends to be dissipative, and it takes the charge off the surfaces. When you do frequent cleaning, you get rid of that conductive film, and the contamination now deposits on your product surfaces. The act of cleaning and wiping surfaces can itself result in triboelectric charging of insulators. If you have an insulator that you're cleaning to keep your surfaces, free of contamination, that itself can result in triboelectric charging of the surfaces. I don't know, those of you who are old enough to remember CRTs, remember at home, if you happen to have your CRT in a place where the sun could come in, you could probably see particles moving around in the air near the surface of the CRT. Now, take a wipe and wipe down that CRT. What you wind up is charging the surface of that glass CRT. And the result is, if you watch the particles in the air near the CRT, they move around until they come close to the surface, and then all of a sudden they're attracted to the surface. Whereas before, they were just wandering around in the air. So charging that surface is the result of more contamination winding up on the surface.
Okay, Arnie, we have a couple more questions here.
Okay, let's take them.
What is let's see, let me go back up here. Does airflow cause charging?
Good question. Go ahead, is there more?
Yeah, and this person followed up by saying that some of the factories claim that it does.
Okay. The reality is clean air does not cause tribocharging, does not cause charging. If you have particles in the air, it will most definitely cause tribocharging. So if we're doing a process that involves some kind of particles for, say, perhaps cleaning, you actually want to use those particles for cleaning the surface. The result is that you may clean the surface, but you're also going to charge it because of the particles in the air. Air alone does not cause tribocharging, period. Air with contamination in definitely causes tribocharging. So I've heard this comment made by many places that air is causing tribocharging. What we've always found when that claim is made, that what the air is doing is actually causing the surface to vibrate. The vibration is motion. It's contact and separation. And the vibration caused by the airflow is what charges the surface. But the air itself does not charge the surface. Contamination in the air, vibration caused by the airflow, those can cause tribocharging of the surfaces, but not the air itself. Hope that answers the question.
It does.
Okay.
I have a couple more. Do you want to handle them now or later
Sure,
on?
let's take them now.
What is the recommendation to reduce wafer spin dry process? Ultra clean water friction static charging.
Okay, let me go back to that slide. All right, now, this is a spin rinser dryer. What you see mounted up here is an air ionizer. The nitrogen that does the drying, instead of going straight in to the spin rinser dryer and causing static, static charging of the wafers during the drying process. Instead, you ionize the nitrogen as it comes into the spin rinser dryer, and the ionized nitrogen makes sure that there's no charge being generated during the drying process. So there is a way. This is one particular type of ionizer that's very useful to do this. There are other types of ionizers. We have seen ionizers that are placed directly in the bowl, where they put emitter points from an ionizer in the bowl of the spin rinser dryer. Those seem to last maybe a year before they fail. Water and high voltage are not a good combination. It's better to have the ionization done outside of the bowl of the spin rinser dryer, and that way you don't have a failure of the ionizer caused by the liquid in the process. So that is the way that we make spin rinser dryers into equipment that does not cause static charging. Does that answer your question? Well,
Seems like it.
seems like it does. All
Yeah.
right.
We have another one if you want to take it now or later.
Sure. Let's take them as we got them.
For manufacturers of medical devices in clean rooms, currently these companies, the compliance to S2020 is voluntary. Do you foresee somewhere down the road that the FDA will mandate adherence to 2020?
Mhm. Well, here's the thing. The answer is it's possible. The problem is that the FDA has a set of rules that they call GMP, Good Manufacturing Practice. Okay? It is almost impossible to change those rules. The medical device industry has been using those rules to protect themselves from any kind of lawsuits caused by failures of their product. What they're basically saying, we manufacture this using the FDA's GMP, and we are complying with all of the rules that the industry has. Changing those rules is very, very difficult. So while it is possible that they may adopt S2020 in the future may be a long way off.
And I would add to it, S2020 is not mandatory outside the clean room either,
Yeah,
unless your customer requires it.
right. Mhm.
And there's another one here on, so if using clean compressed air, does that mean you don't need an ionizing gun?
Okay, well, if you're using clean compressed air, and I'm going to assume that you're using it because you want to blow particles off a surface.
Yes.
Yes, okay. It will still work. However, if the surface happens to be charged, it's going to be very difficult to remove the particles that are on it. Ionizing the clean air that is being used for blow off will improve the efficiency of cleaning.
Okay. Yeah, clear. Yeah, thanks.
Clear? Okay, thank
Yeah,
you.
yeah.
Is that it, Ted?
One more.
One more? Okay.
Ionizers on spin dry process would potentially have water flash on the emitter and cause the ionizer emitter to be short or damaged. Any alternative ionization?
Yes. I mean, that's what I was talking about before, that there were some spin rinser dryer manufacturers that tried to put ionizer emitter points in the bowl, which fills with water during the cleaning process. And most of those ionizers failed in a year or less. They were not a good idea. The other ionizer I showed you, where the ionizer is actually outside the bowl and is just ionizing the nitrogen that goes into the bowl during the drying process, that's the kind of ionizer that will last you essentially forever. So basically, you don't want to put emitter points in the bowl that fills with water in the spin rinse or dryer, because eventually the water and the combination of the water and the high voltage will cause the ionizer to fail. Better to put the ionizer outside the bowl.
Good, that's the end of the questions so far.
All right. So as I was saying, the act of cleaning and wiping of surfaces can itself result in tribo-charging of the insulators if the surfaces are insulators. So you want to be aware that that's going to happen. Now, process required insulators. That's why we have a problem with insulators. In our manufacturing, different manufacturing uses different, insulators, but we see glass plates. We see our lithography reticles. These are the negatives that make the patterns on the wafer. The IC and component packages are epoxy. So that's an insulator that can charge. Our printed circuit boards are insulators, and they can charge. If we have to store chemicals and use it during a process, the chemical containers themselves are usually insulators to keep them from, reacting chemically with their contents. Wet process surfaces, anytime you have a surface that has water on it and you physically remove the water from the surface, it causes charging. Oxide-coated wafers are insulators, they can charge. FOUPs and FOSBs, these are the what we call these are the carriers for our wafers. FOUPs are used in 200 millimeters. FOSBs are in 300 millimeters, and I am not going to even try to tell you what those acronyms are. Enclosure materials, if you have, a tool that's in an enclosure, most likely the enclosure materials are going to be insulators. And then in some processes, you're going to use plastic films and tapes. These are all insulators. You cannot remove static charge from these materials by grounding them. Insulators cannot be grounded to remove static charge. You have to, the only way to remove static charge from an insulator is basically to use some type of ionization to remove the charge from the insulator.
We have another comment or question here, Arnie.
Sure.
It's really a comment, but I know you'll want to elaborate. Polonium-210 ... a bit scary.
All right. Polonium-210 is this is an alpha emitter, and alpha particles interact with the molecules in the air and cause us to have pairs of ions produced. So the upside is that the polonium is used in ionizers in places where you don't have power available, where you might have a flammable environment. There are lots of places where having an ionizer that does not use electricity is a positive step. Now, polonium-210 emits an alpha particle and decays into lead. So the result of the radioactive decay in polonium is that you have an inert material. So you're not left with a material that in itself is still radioactive. Polonium-210 is an alpha emitter. Alpha particles do not penetrate your skin more than 40 microns. Okay, the live cells beneath your skin are approximately 120 microns below the surface. So the polonium-210 alpha emitter cannot emit radiation that gets into live tissue from the outside of the body. Okay? Now, You've heard of polonium-210 being used to poison people. And the way they poison them is they ingest it. Now the polonium-210 is in live tissue. It's in your stomach. You might inhale it into your lungs. It's in live tissue, and now the radiation can cause serious damage to your body. But polonium-210, as it's used in ionizers, as it's, you basically follow the instructions for using it. There's no, indication that there's any danger from this. And polonium-210 ionizers have been used for probably more than 40 years in many industries, besides the cleanroom industry. So, polonium-210, not quite as scary as you might think, and it certainly, if it's handled correctly, is not a hazard. The basic rules for using radioactive materials: don't burn it, don't smoke it, don't eat it. If you follow those rules, you're pretty safe. Hope that answers your question. Okay. So clean rooms require process. There are insulators required to do the process in the clean room. And in general, they're made from insulators. You can't ground the insulator. You have to use ionizers to neutralize them. So one of the things we can do in the clean room is to use low particulating static control materials. We want to get rid of the insulators. We want to use materials that are static dissipative or conductive so that we can connect them to ground and make sure they're not charged. So there's a variety of materials. You see a list here: conductive polyurethane, ESD fluoropolymers, ESD Torlon, carbon-loaded PEEK, low-carbon polyolefin, carbon-loaded Vespel, natural nylon, some ceramics, and doped silicon. These are all low particulating static control materials. You can use them to make sure that the materials you're using to handle your product are generally not ones that are going to become charged and attract contamination. So what does clean room ionization look like? This is one version of clean room ionization. You see the positive and negative emitters connected to an ionizer control system, which is above the clean room ceiling. You just see the ionizer emitters through the ceiling here, positive and negative. So this is one method. This is a room where you have your controlling static charge to make sure that the product that's handled by these machines does not become charged and attract contamination. Slightly conductive air caused by the ionizer drains the surface charge and reduces the particle attraction. Here's another version of a clean room ionization using bars. You have a series of bars. Each bar is, I think each pair of bars is mounted above, Each pair of bars is mounted above one of these machines here to make sure that anything handled by this machine, it does not have a static charge on it. Ionizer installation. Now here you see the complete ionizer, the control system, and the ionizer emitters. You have them in the ceiling of the room. And this is this is a piece of equipment that's in the room. And you see in here, in the back here, you have an ionizing bar to make sure that things within this machine are not becoming charged. So what you want to do for your ionizer installation, you want to install ionizers in the room as well as in the tool. Obviously, room ionization out here is not going to get into this equipment enclosure. So you need to put ionizers in the equipment enclosure itself. So how do we engineer cleanroom ESD control? And this is also for cleanroom ESA control. First of all, we ground everything that is conductive, including people. That's why people wear wrist straps. We want to ground them. That's why they wear foot straps. We want to ground them. So we want to ground everything that's conductive in the room, including the personnel. We want to use low charging, grounded, static dissipative materials whenever possible. However, we have to be sure that the materials we're using are not going to compromise the clean room requirements. So that basically you want these low charging, static dissipative materials, but you don't want them to be emitting particles. So we need to make sure that there's no compromise in the cleanliness requirements. We want to avoid metal-to-metal contact of charged ESD-sensitive devices. This is ESD control. An ESD event happens from metal-to-metal contact. So if we want to avoid ESD damage to devices, we want to avoid metal-to-metal contact. And finally, we want to properly utilize air ionization. We want to make sure that we put the ionizers where they are neutralizing the charge on surfaces that may attract particles. We want to make sure that we are removing the static charge in places where an ESD event might happen. And one of the things we always say about using air ionization, try it out. Make sure that using ionizers actually does something for you. Excuse me. We want to make sure that, that the ionizers actually do something. And if they don't do something, you don't need to use them. So always ask the ionizer suppliers to provide you with test ionizers that you can use to determine whether the ionizers are actually going to solve your static problem. And one more thing that we always have everywhere where we're trying to do static control in the clean room, we want to do personal training and program auditing. Basically, increased awareness helps to eliminate problems with personnel training. And if you're not auditing your program, you're lying to yourself that you have a static control program. Auditing is a really important part of having a static control program, and the work we do at training people for TR53, that's the auditing document from the ESD Association. And basically, if you're not, you've got to do program auditing. There's no option here. That if you're not auditing your ESD control program, you don't have an ESD control program. And finally, to summarize, what we talked about today, particulate contamination is hard to remove, and it gets harder to remove the longer it remains on surfaces. So you want to get your particle contamination off the surface as quickly as you can, and using ionization in your blow-off operation is an improvement in the contamination control. It will basically get the charge off the surface, get the charge off the particles, and make sure that particles are not re-attracted to the surfaces. The forces of electrostatic attraction often exceed the attraction due to other forces. That you saw from that one slide, that if you have even 200 volts per centimeter on the surface, which is a very low static charge level. For particles less than 1 micron in size, electrostatic attraction is the major force that attracts particles to the surface. And remember that controlling ESA, electrostatic attraction, requires a combination of contamination control. You need to reduce the amount of particles in the room. You need to reduce the number of particles being attracted by static charge. That your control of ESA is a combination of both contamination control and static charge control. I think this is the last slide. Does anybody else have any other questions we can handle for you?
Yeah, we do have a couple more here.
Okay, all right, let's do it.
One is regarding FOUPs and FOSBs
Mhm.
made out of anti-static material. Are they are they a problem in terms of clean room perspective? Could they be doped or with carbon powder or other chemical in the surface that
Mhm.
could degrade? And is it preferable to stay with the high charging version and use ionization?
Mhm. Well, it's definitely an improvement in your static control to have FOUPs and FOSBs that are made out of inherently dissipative material. There are plastics that are used to make these carriers that are that will give them permanent static dissipative resistance if you were to measure the surface of the material. Um, it makes things better. There's no question about it. You can get away with using ionizers and insulative carriers, but it's better to have them be static dissipative. And in fact, um, some things like the reticles in photolithography are even, should even be carried around in enclosures that are conductive. That's preferable. If the carrier is static dissipative, you might have a scenario in which you can still get ESD events happening to the photolithography reticles in the carrier. It's better with reticles to have a conductive carrier. When you're taking wafers around, a static dissipative carrier is definitely preferable to a insulative carrier from the point of view of particle contamination.
Okay.
Next question.
Yep. The next one is in circuit board production. The comment is that the particle contamination is a big issue since the charge can be significant on a board. The
Mhm.
factories using some of the factories are using air ionization. Is it really effective? Because I see it normally is not a clean room, a clean room class
Right.
operation.
Yeah.
And last part of it is air ventilation is not really not effective for every area and may not cover everything.
Mhm. Well, as far as circuit boards are concerned, if there is a contamination issue, and I'm not sure what that contamination issue might be with a circuit board. Usually, circuit boards get cleaned at several steps in the process, and they generally tend to not be a contamination issue. But if there is a contamination issue, using ionizers will make it easier to get the contamination off of the circuit boards. So there is a scenario in which having an ionizer around the circuit board will reduce the amount of contamination that winds up on that circuit board. I'm not sure where that might be a problem, but if it is, definitely ionization to take the charge off the insulative material of the circuit board will make it easier to clean.
Okay.
Okay.
Another one is regarding room ionization having a poor balance or significant offset.
Mhm.
And therefore this individual is less prone to choose this option.
Mhm.
How does this impact ESD class 0 devices?
Okay.
Do we need
Well,
specific
yeah,
ion
go ahead.
sources and zones?
Mhm.
And then the last part of it is a room with ion bar system, um, a local area with good balance ionizers.
Mhm. Okay. Well, good balance in the ionizers is important if you are trying to handle very ESD sensitive devices. Uh, when you're talking about, semiconductors, you're talking about 200 to 250 volt sensitivities are not uncommon. When you get to disk drive, you're talking about 1 volt sensitivities to ESD that, obviously mean you have to use very well balanced ionizers in these areas. Um, the When you're doing contamination control, generally, if we can reduce the charge on the surface below 500 volts, we've probably taken care of most of the problem. Certainly, if you can get it under 200, and we're talking about, 500 volts per inch, not per centimeter. If we're talking about, keeping things clean, you don't need to have a very well balanced ionizer to do that. An ionizer balanced to, plus or minus 100 volts is fine for contamination control. If you have a class 0 device, plus or minus 100 volts might be okay, but it might not be okay. You might need plus or minus 10 volts. You might need plus or minus 1 volt. You might need 0 volts. You might need to use polonium ionizers, which, are always at zero balance. So basically, if you're doing contamination control, you don't need as well balanced an ionizer. If you're doing ESD control, you may need a very well balanced ionizer. So there's two different requirements there.
Good one. Another one here is, let's see, directing the ionizer airflow directly at a circuit board can damage sensitive devices. Ionizers are designed to neutralize static charges on insulating materials by emitting positive and negative ions. Please advise on this concern.
Mhm. I haven't had an experience where ionizers that were well balanced caused damage to anything, any ESD sensitive parts. You do have to make sure that the ionizer you're using is compatible with the product you're trying to protect. In other words, an ionizer balanced to plus or minus 100 volts is not of any use in a disk drive situation where you need to have, plus or minus 1 volt balance. So basically, this is an ionizer selection question. And basically, you select an ionizer whose operating characteristics are compatible with the product you're trying to protect. If all you're concerned about is contamination control, an ionizer balanced to plus or minus 100 volts is fine. If you're concerned about disk drive, you need an ionizer balanced to 1 volt or less. If you have a semiconductor device that's sensitive to 200 volts, a plus or minus 100 volt ionizer is still, again, okay. So you have to choose ionizers whose operating characteristics are compatible with the product you're trying to protect. And not all ionizers will work with all product. You do have to, make choices, and you have to choose ionizers that are compatible with your needs. Fortunately, when it comes to electronic ionizers, there are some methods available to, make sure that the balance remains stable and can be balanced to, very low levels. So basically, there are methods and ionizers that will work for practically any application. But as I said before, you always want to try out the ionizer in your own factory, in your own usage of sensitive parts, and make sure that the ionizer actually does something for you, that it removes static charge, it doesn't damage your product, and it basically works to solve your static problems, whether they're contamination or ESD related.
The next one is regarding decay times and recommendations. This individual has seen a variation between 20 seconds and 2.5 seconds,
Mhm.
and there doesn't seem to be a standard defining that.
Mhm.
He has some recommendations that cutting the it's hard to read here. Some could just keep trying to cutting it by half as a tightening control without good fundamental reasons.
Mhm. Well, you're right about one thing. There's no standards for decay time. Uh, Decay time will depend on ionizer placement. It will depend upon the speed at which the product is moving when it's under the ionizer. Um, there are several requirements for ionizers that will affect the decay time. Um, all I can say to you is, in most cases, if you can achieve a 10-second decay time in your application of ionizers, you're probably doing fairly well. Okay, there are applications where the ionizer works very well with 45 to 90-second discharge times. There are applications of ionizers that require discharge times of 5 seconds or less. So your application of ionizers is going to determine what your decay time needs to be. There are no standards out there that tell you what to choose. The choice of the decay time is really up to you, and you're going to choose it to make sure that the ionizer solves your static problem. So that sometimes you need to solve an ESD problem that occurs when the product is handled, and you may need to have a very fast discharge time to solve that problem. If your problem is long-term contamination attraction, um, the ionizer may not need to be controlled better than 100 volts. 100 volts would seem to be fine, and maybe a 1 minute discharge time. That seems to be fine for controlling static charge. You don't need things don't happen when it comes to particle attraction. It's a long-term effect. I mean, you saw in the analog devices testing that to get a significant number of particles, you have to wait 6 weeks, 1,000 hours, so that basically if your discharge time was 1 minute, 5 minutes, 10 minutes, all of those would be okay for controlling ESA, because the ESA problem happens over a long period of time. So, um, you know, uh, there are lots of ionizers out there. They all have different operating characteristics, and you just have to choose the one that meets the requirements of what you're trying to do. If it's ESD control, the discharge time will tend to be fast, usually 20 seconds or less. Um, if it's uh, if it's control of static charge attraction, ESA, it could be 1, 5, 10 minutes. That would be fine also for solving that problem. So basically, different problems, different ionizer requirements.
And this next question on is related to that. It's just saying, what is the recommended ionizer performance analyzer test time?
Mm-hmm.
60 seconds, or is there a better choice?
Well, the ionizer test time definitely relates to the type of ionizer you're using. In a room ionizers typically have anywhere from 30 to 60-second discharge times, so that you're basically, that's what you're looking for, and you have to check your ionizer. Generally, you spend 1 to 5 minutes measuring the balance. so that you know the ionizer is balanced for positive and negative. Um, it's not necessary to check an ionizer for 1 minute if it has a lot of airflow. If it's an ionizing blower or an ionizing blow-off gun, the actual test time can be significantly less than 60 seconds. Uh, Typically, with a blow-off gun, you're expecting discharge times in the 1 second and under range, so you don't have to test for a minute to check the balance. That a few seconds is enough. With ionizing blowers, you expect that the discharge time will be anywhere from 1 to 20 seconds, and you don't need to test for 60 seconds to determine the balance of the ionizer. You can do it much quicker than that. But anyway, the bottom line here is that different ionizers have different operating, characteristics. They will have different test times. The controlling document here is ESD STM 3.1, which is the basic ionizer test document, and it will have recommendations for test times for the various types of ionizers. And you can use that as, what it's going to tell you is the test time. It's not going to tell you the required discharge time. There are no documents that do that. So the discharge time you require depends upon your operating characteristics, speed of motion, distance from the ionizer. These are all the things that, affect what type of ionizer you use. And, there'll be different requirements for different applications.
Okay, we have two more.
Right.
After the product is manufactured, is it necessary to have an ionizer in the shipping and inventory storage areas when handling, packaging, and shipping ESD-sensitive components?
Generally, what we tell people is if you have ESD sensitive components, you should use, static dissipative packaging materials. Once your ESD sensitive component is within the packaging materials, there's no need for any other static control requirement. The static dissipative packaging material will protect that ESD sensitive device, and you don't need anything else. You don't need ionizers. You don't need grounding. You basically don't need anything else other than that static dissipative packaging material.
Okay. And the last one has two parts, actually. Is a chair mandatory for personnel grounding at seated operations and with a wrist strap connected to a real-time constant monitor?
Okay. If the person who's doing the work is seated, S2020 mandates they must wear a wrist strap. There's no options there. Now, when it comes to seating is a backup. In other words, if you have a static dissipative seating and it's properly grounded, it is a backup for the wrist strap. In other words, if the wrist strap were to fail, you still would have your personnel grounded. And there are situations where if an ESD control method fails, you have to throw away the product that was being worked on. If you have a backup, like an ESD chair, you might not have to throw away the product that was being worked on. But once again, S2020 mandates that all seated personnel must wear wrist straps. That is the primary method of grounding, and anything else is extra, or it's an alternative that doesn't meet the extra requirements. In other words, people can wear dissipative footwear, and you might have a dissipative floor, and that would be very good when people are walking. But once again, even with a dissipative floor and an ESD chair and dissipative footwear, those are all backups for the requirement that when someone is seated, that they wear a wrist strap. So that's the primary method of grounding people when they're seated is wrist straps.
Thank you, Arnie. One more. What is the clean room garment fabric particle filtration and conductive grid size for effective use for classes, I assume it's clean room classes 5, 6, 7, and 8.
Mhm. I really don't have a lot of experience with the design of clean room garments. So it's hard for me to give you an answer to, the specific requirements for the clean room garment material. There are clean room garments that are usable in class 1 and, or ISO class 3 or better. And so it doesn't seem to be a problem. The material, to reduce particles, people usually enter the clean room through an air shower that helps remove particles from the garments. We have had situations where we were asked to install ionizers in the air shower to improve the particle removal of the air shower. I have anecdotal, information that seems to work, but I don't know of any, significant testing that was done to verify that. So basically, when it comes to clean room garments and their material, there are, clean room garments and materials that are suitable for ISO class 3 and better. And, it doesn't seem to be a significant problem to make those garments. The issue that sometimes comes up is that you'd really like to be able to ground the garment. And there are clean room garments that are groundable. And that sometimes helps in controlling static charge. But that's a different type of material that has usually a grid of conductive fibers woven into it. And that allows you to actually ground the garment, whether it's directly or through the clean room booties that touch the floor that can possibly ground the garment as well. Sorry, I don't have a better answer for the specifics of your question, but that's all I can tell you about garments.
Okay. I think we'll take one more question here and then we'll wrap it up. This is working seated. The use of wrist straps is mandatory. However, often operators forget to wear them. Cheat the connections on the continuous monitor and cheat the. They find a way to work around the constant monitors, I guess.
Right. I've seen several of those workarounds.
Yeah.
Well, as I said, S2020 mandates that seated personnel wear a wrist strap. And it's best, if you have very sensitive devices, that wrist strap is, attached to a constant monitor that tells you whether the wrist strap is working or not. There are very clever ways of defeating all of this. But the fact of the matter is that, one of the things that your auditors should be doing, is, what we always recommend that you do auditing, just, drive-by auditing, we call it, where you just do a walkthrough every day. That's one of the things the auditors do, is that they go through the factory every day and look at the ESD control methods and make sure that they're being followed as directed in the company's policies. People will always try to cheat. People don't like being tied down. They don't like wearing wrist straps. This is a fact. But the other fact is, to protect your product from ESD damage, these things are required. So basically, you can check up on people, do a daily audit, do a walkthrough. They don't know when you're coming. they're gonna stop cheating. But basically, people will cheat, and there's nothing you can do except keep a vigilant eye on it. Have managers that go around and check their personnel in the areas that they're responsible for, and basically make sure that the ESD control methods are being followed. If they're not being followed, the possibilities are there that you're going to have product damage. You catch that in your final test. You're going to have product damage that you don't catch right away in final test. And, if the ESD control methods had been followed, you would not have a problem. So basically, the answer to what do we do about that is, you just have to be vigilant. You have to make sure that your auditing process catches things like that, where people are either, on purpose not following the requirements because they don't like them, or there's something that's happened and whatever the ESD control method was, it failed for whatever reason. And being vigilant means that you'll be able to find that failed ESD control method in as short a time as possible.
I can augment that, Arnie, by explaining what I call the secret sauce. This is something I learned the hard way. And for those who may or may not know, when I was working for Lucent Technologies, I was responsible for a facility with 12,000 people and 2 million square feet of floor space. And I tried every compliance strategy that I could think of, and eventually developed what I call the secret sauce. It's a carefully planned statistical sampling strategy. And unfortunately, we've run out of time, so I can't really get into it in depth. But if there's enough interest, we could, or if you want to contact me later, we can talk about it. Or we could set up another webinar to do that. And
Yes. Sorry to interrupt you. Yes, this point is very important because I think there are two very different situations. One is the component production, and another is the EMS. And for instance, I work in the appliance business. We are now in a situation that we are, let's say, doing a migration from mechanics to electronics. Yeah. And so people are not so skilled and you know very well. So you don't see the static electricity. So you really need to be, of course, people need to have the training, but nevertheless, it's not really easy to do this regular audit. Previously, in my previous job, I worked to Bosch in automotive. Yes, and then I was daily in the plant, and it was possible me to trace and to press, but nowadays not possible. And what I will realize in my visits to my EMS suppliers is really, so there is a mixed and also a migration from people working seated and standing. And it's really tough to the people to go pick up a box, place it in the workplace, then finish the job, or going to position A to position B. But time to time, maybe the production increase, they sit, and finally I would say basically people forget to connect. Also happens a lot in the labs. Yeah, hey man, can you come here? Yes. Then 1, 2, 3 times, the third time they just forget to connect. Of course, we can use tailoring, and I really normally to my customers I recommend to, in this situation, I think better to use the tailoring and force the situation, the protection. Also, as example, the clothing and the EST chairs to help, let's say, to ensure this connection, because I think I'm strongly thinking and pressing that we should change S2020 and IC in order to, let's say, force the people to have, for sitting and standing, the same request. Below 1 gigaohm, below 100 volts, of course, depending the needs, but let's say in a standard way, and should be possible and not mandatory to, because, you know, for some people, it's, they follow real the guideline, because then there are no deviation, nothing to justify. And very often we find really people, finally they are not wearing the ESD shoes and the flooring, and they are not wearing the wrist strap, and this is the worst of the two worlds. Yeah.
Well, it's all good information. Again, the technique I developed, I was able to get 12,000 people in lockstep with almost perfect compliance to all of the procedures, whether it's grounding or using the right materials. But again, to explain that properly, it would be another webinar. It takes about an hour to really explain the concept.
Yes.
But it works beautifully and has invariably worked well.
Yeah, I was very interested. You know, your comment about the appliances going from mechanical to electronic. You know, it's gotten to the point where I feel like I need an IT department to operate my washing machine.
Yeah, it's true.
It's gotten much more difficult. That the changeover from mechanical to electronic has not been an easy one.
Yeah. Yeah, but
But you're right.
yeah.
I mean, you know, the fact that you have much more electronics in these things means that you have to be much more careful when you're doing your manufacturing to make sure that you don't, you know, damage, you know, cause ESD damage to the electronics. And you know, what we're always concerned about is premature failures. That, you know, basically,
Yeah.
the failures that occur in the manufacturing area, you catch those, you replace whatever parts need to replace, and you have a working device. When it fails in the customer space, you have an angry customer, and that's not what you want. So you basically want to make sure that you don't, you know, have a situation where you might be causing ESD damage that doesn't cause an immediate failure, but causes a failure somewhere down the line.
Yeah, sure.
And you know, the thing I talked about, you know, just briefly, of course, was